Today we will be discussing motors and how torque applied to current loops makes them possible. People use motors many times a day, often without realizing it. As you watch this video today, you are likely using two motors, one that provides energy to your computer's hard drive and the other that works the cooling fan in the device. So when you wake up in the morning and use an electric toothbrush or an electric shaver, blend up a smoothie for breakfast that you take out of your fridge and later place in your dishwasher, know that you've just used a handful of objects that you wouldn't have if the physics behind motors had never been discovered. So let's get into the simplified physics of how a motor works. As you can see from the pictures on the right, a motor can be simplified down into about three main parts, which are the rod, the coil, and the magnets. So the rod essentially helps to turn the coils and keeps everything in place. It also can have the current run through it and then attach to the coils. And the coil, it ends up getting the current and becomes attracted to the magnets and helps to spin and to conduct electricity. Then we also have the magnets, which they create the magnetic field for the coil to be attracted to. And so the basics of how a motor will work is that the current will be running through the coils, and that makes the coils want to align with the poles of the magnets. And every time that the coils are about to align with the poles, the current is made to change, which then causes the coil to then have to rotate even more, trying to align again. And then the current, it just keeps changing each time that the coil is about to align, and that is what keeps the motor continuously running. So obviously, motors are much more complicated than just this picture on the right, but it really helps to learn the basics of something before going into the more complicated physics of it. Okay, so when working on motor physics problems, you will want to know the direction of the magnetic field and the electric current that is flowing through the motor. And an easy way to tell the direction of either of these two components is to use the right-hand rule. To perform this, you will need to be given one of these two components, either the direction of the electric field or the direction of the magnetic field. So once you're given one of these, and let's say that we'll just work off of this photo that's in the slide. So let's say that the electric current is moving upwards, and we want to find the magnetic field. Pretend that you don't already know the direction that it's going. So an easy way to tell is to use the right-hand rule. And so since we have been given the direction of the electric current, the trick is to put your thumb facing the direction of the electric current that you've been given. Now that you've been given the direction of the electric current, look at your fingers and see which way they naturally curl. In this instance, they curl counterclockwise. And so this is just a quick trick that you can take into a testing center and can just know on the spot the direction of some of these forces. And it's actually really helpful, especially when you are just trying to first visualize some things about how the motor is working before you get into the math. Okay, another important thing for you to understand when you want to work with motors is the torque equation. The torque equation shows the components of a motor that affect how it works, and we'll break down the equation into each portion. So T equals torque, and the torque is the twisting force of the inner motor components that tend to cause rotation. Next we have N, and this is the number of times that the coil of wire is wrapped around the rod. I is the electric current that is felt by the coil in the presence of a magnetic field. A is the area of the motor components. B is the magnetic field that is created by the magnets. And the sine angle is the angle of motor components. Whoops. Okay. So now we're going to jump into a torque practice problem. And it goes as follows. What is the maximum torque on a 150 turn square loop of wire that is 18 centimeters on a side and carries a 50 amp current in a 1.6 Tesla field? So remember the torque equation. Maybe pause and try to figure this out by yourself, because now that you have the torque equation, this should be pretty easy to just plug and chug. Okay, here is the solution. So first, something that we should note is that the maximum torque will be found at a 90-degree angle. And if you've taken trigonometry, you should just know this, but if not, that's generally the rule. So then down below we have the torque equation, and we can plug in the different components that we were given from the question, such as the 150 turn is N, the 50 amps is I, and then B is 1.6 Tesla. And then for A, the area, we know that, so we're told that for this motor, it's being created by a square loop of wire that is 16 centimeters on one side. And so we know to calculate the area of a square is just one side times the other, and the units will be then meters squared. So 18 times 18 is 324, and then you convert that from centimeters to meters, making it 0.0324 meters squared. And then after we plug that all into the equation, what we get out is 388 Newton meters is how many torques this motor has. Okay, so now that we have the torque equation, we know how to work it, we know how to make a really strong motor. And as I was researching this topic, I looked up on Google just some of the most strong motors in the world, and what popped up were really large in size motors. And it was a little surprising at first, but it really shouldn't be, because we know that in the torque equation that area is a big component of that, and the larger the area of the motor, the more powerful it can be. So not every motor will be super large, but I thought that that was a cool note to see that some of the most powerful motors in the world for like planes, engines, on trains or ships are some of the largest ones in the world, as we can see on this motor. Okay, so you now have the knowledge of motors basics, and you know how to calculate the torque of a motor, quickly determine the direction of some of its forces, acknowledge the physical components of a motor as well as the mathematical components that work in tandem to create strong motors. So thanks for tuning in. See you next time.